By now you know how to calculate the end-to-end delay of a packet across a network, and you know that the queuing delay makes the end-to-end delay variable. Most of the applications that we use don't particularly care about this variability in end-to-end delay. For example, when we're downloading a web page or sending an email, we want it to complete quickly, but we don't particularly mind if individual packets take 10 or 12 milliseconds to reach the other end. But there are some applications that really do care. They have to care about the queuing delay, particularly what we call real-time applications like streaming video and voice. So let's take a look at an example. Over the next few minutes, I'm going to explain why queuing delay makes life hard for these applications. It serves as a good illustration of queuing delay and how we might mitigate the problem in practice. Basically, because the applications don't know precisely when the packets are going to show up, they can't be sure they will have a voice or video sample in time to deliver it to the user. And so they build up a reserve of packets in something called the playback buffer. So we're going to take a look at playback buffers. You've actually all seen a playback buffer before. This is a little screenshot from the bottom of a YouTube client. And the red line on the left over here, this shows the video that we've already watched. This here is the point of playback. This dot shows where we've got to. And this area over here is this gray line shows the video that has been buffered, or the packets that have been buffered, that have not yet been played back to the user. And this is the part that we're going to be interested in. This here is the playback buffer. So the client deliberately tries to build up that playback buffer to try and get ahead, just in case some of the packets are delayed or they don't arrive in time, and in case there's some kind of temporary outage. So when designing the playback buffer, we have to think about how far ahead we want the buffer to get. So if we were to build up the buffer all the way over here and build up more packets, then we've absorbed more data and we can write out more variability in the queuing delay. If we make it very short down here, if there's a big change or a big change in the queuing delay or a sudden increase in the queuing delay, we may run out of packets because they may not show up in time. So designing this playback buffer is pretty key to making this application work. So how much we want to accumulate in the buffer when we start playing back the video to the user is key. So let's take a closer look at this. This is the point that we're playing. This is the amount that we've buffered. This is the contents of the playback buffer. If we look down into a little bit more detail, so we're going to take as an example this setup here. So imagine we're watching a YouTube video on the laptop on the right, so over here, and it's streaming video from the server, the YouTube server, on the left over here. So we're going to assume that the video is being streamed at 1 megabit per second. Now this is just a made-up number. There's all sorts of rates that it could be streamed at. This is just going to make it easy for us to think about. And it's going to pass through several routers along the path, 1, 2, and 3 on the figure here, but it could be many more than that. It'd be very common for our packets to go through 10 or 15 routers on the path from YouTube to our client. And the thing that we're going to be concerned most about is the queuing delay here. So there's 3 places where we can experience queuing delay, and that variable queuing delay is going to mean that our packets show up at slightly unpredictable times. So let's look at a graph of what this might look like. This graph shows the cumulative number of bytes sent by the server over time as a function of time. Because it's sending at a fixed rate of 1 megabit per second, it means that the line is straight. The cumulative number of bits or bytes that it sent as a function of time is a straight line. And so after 1 second, it will have sent a megabit, a million bits, and after 10 seconds, it will have sent 10 million bits. Because of the variable queuing delay in the network, the cumulative arrivals at the laptop look a little bit different. They might look like this. So you see this wiggly line that I've got here. what does this mean? It means that if we take the first byte here, because they're all arriving in first come, first serve order, we can just draw horizontally across here and see when a particular byte arrived. So this one arrived here after that delay. So the x-axis is going to tell you how long that particular that particular byte took to get there. Notice I'm saying bits and bytes. It doesn't matter what our units are here. So if we would take any point on here, let's say this particular byte, and we draw horizontally. I'm not very good at drawing straight lines, but that's supposed to be horizontal. And right here is the time at which that particular byte arrived at the laptop. So you can see that the delay is measured by the horizontal distance, right? The horizontal distance here. And you can see that it's a variable number depending on the queuing delay encountered by each of the individual packets. We can also see at a given time, how big the amount of buffering along the path. Basically, how many bytes are in the path from the server to the client. And that would be shown by the vertical distance here, because it says that at a particular time, this is the number that have been sent, and this is the number that have been received. So we can tell quite a lot of information from this graph, and we're going to be seeing some more examples of this type of graph later. Horizontal axis is the delay. The vertical axis, it tells us how many bytes are buffered right now in the network. Okay, so let's get back to our example. So the biggest component of the delay is the propagation and packetization delay. That's the fixed component. So we actually know quite a bit about the shape of this line. So the actual shape could look very different. I just made up this shape. However, we do know a couple of things. First, the overall end-to-end delay can't be less than the packetization and propagation delay. They're a lower bound. So this has a lower bound in the horizontal distance between the two here. Whoops. It also has an upper bound. So the buffers in the routers, the packet buffers here, they're of finite size. So there's a maximum delay that any packet can experience going through one of those buffers. So if we add up the maximum of each of these, add it to the packetization delay and the propagation delay, it's going to represent an upper bound. So we have a lower bound and we have an upper bound. But the upper bound is not very useful because it can be very, very large. In practice, these routers may have half a second of buffering. So if we're going through many hops, it would mean a ridiculous difference between the lower bound and the upper bound. So that's of not much use to us. We also know that the cumulative arrivals on the right-hand side are non-decreasing. In other words, this value is always increasing because it's the cumulative number of bytes, and obviously we can't have a negative number of bytes show up. Finally, one more thing that we know is because we know how fast, or there is an upper bound on the rate of that last link, it could be a 100 megabit per second link or a gigabit per second link, it tells us that the instantaneous arrival rate here, the gradient of this line here, can't exceed the speed, the data rate of that link. Okay, so with all of those caveats, let's look at what the client actually needs to do to make all of this work. So this red line here shows the playback rate of the video to the user. So this, what this tells us is that at this time here, it's playing back the first byte that was sent by the server, which is of course the first byte received by the receiver. So if at any point we take a horizontal line across here, it will tell us the time that a particular byte was sent, received, and then played back. What that means is that the horizontal distance here tells us, so for example, in the horizontal distance here tells us how long a particular byte has been buffered. So at any one time, we can tell how long it sat in the playback buffer before it was played back to the receiver. We also know how many bytes there are in the playback buffer. It's the vertical distance here at any one time. it tells us what the occupancy of the playback buffer is. So we can see that the playback buffer was very small to start with. It accumulates, it accumulates, it accumulates, gets to a very large value here. It then gets smaller as we fall behind, fall behind. Almost goes empty here. We're very lucky that there must have been some bytes that showed up late. We just avoided underrunning the buffer, and then at some time we built up a little bit more, etc. as we go up here. Okay, so we're playing back at a constant 1 megabits per second. That's what's being played back to the user. So this is a good example. We picked the right value, we waited long enough, we built up enough buffer, everything worked out fine in the end. So if we take a look inside the client, it looks roughly like this. So the playback buffer is a buffer held in the memory of the client. The client is picking the playback point. That's this here. This is the point at which it's reached, and that's that dot that we see on the YouTube client. After the bytes have been taken out of the playback buffer, they're put into a video decoder to turn them back into video and then played out on the screen. Okay, let's look at an example of when things don't quite work out fine. So the same example again, bytes sent by the server on the left, received by the laptop on the right. But in this particular case, we didn't wait long enough before playing out the first byte. You can see that here we've waited a little less time from when the first byte was received until we play out that first byte. And of course, once we start playing out the bytes, we're committed. We've got to play them out at 1 megabits per second. Otherwise, we can't keep putting the video on the screen. So on this particular case here, everything looks fine to start with. The buffer has a nice occupancy, nice occupancy, nice occupancy. It gets smaller and smaller and smaller until eventually, at this point here, we have a problem. The buffer goes empty, which means we've got no bytes to decode and put onto the screen. So all of this area here is a time in which we're in deficit. This is not good. What does the client do? Well, we've all seen this before. It has to make the buffer bigger, and it does this by rebuffering, by freezing the screen, waiting for some bytes to accumulate, and so that it can continue. Okay, so if you've been watching a video over this particular video right now over a slow link, or if you're a long way away and you have your packets are going through many routers, you might experience a rebuffering event watching this video. You can fix the problem by streaming at a slower rate, or just simply by downloading the video ahead of time. So in summary, with a playback buffer, when we have packet switching, end-to-end delay is variable. We use a playback buffer to absorb the variation. We could just make the playback buffer very big, but then the video would be delayed at the start. That was the time that we were waiting from the first byte to arrive until we play it out onto the screen. We could make the buffer bigger, but if we were to make that buffer bigger, then we would have to delay the starting point of the video, which would be kind of annoying when we're watching our videos. So therefore, applications try to estimate the delay. They try and estimate the delay from the server to the laptop, set the playback value, and then resize the buffer if the delay changes. Okay. So now let's go back to our original expression for the end-to-end delay. So now we've seen that it has these three components to it: packetization delay, propagation delay, and then the variable queuing delay. And the queuing adds variable and unpredictable delay to the path and to the packets from end to end. Okay, so in summary, end-to-end delay consists of three components. The first two are fixed: propagation delay, which is the time that it takes for a bit to propagate over a link; the packetization delay, which is the time that it takes to put a packet onto a link; and then the queuing delay, which is variable, which is dictated by the time that a packet spends in the buffers in the routers along the path. Some applications, as we saw, use playback buffers to absorb this variable queuing delay to help the applications stream the video back to us at a fixed rate. So this is the end of Packet Switching 2. I will see you again in Packet Switching 3, where I'm going to tell you about a simple deterministic model that helps us understand this variable queuing delay.